Now, let's consider the phase equilibrium of a system with more than one components. The overall system is a closed system with certain temperature and pressure. Thus, the Gibbs free energy change determines the direction of process. The overall Gibbs free energy of the system is the sum of the Gibbs free energy of all the phases. Since mass can flow between the phases, each phase is not a closed system, but an open system. Accordingly, we must modify the expression of the infinitesimal change of Gibbs free energy from a closed system. The Gibbs free energy of an open system depends on the temperature, pressure, and the amounts of substance of all its components. The exact differential of it is like this. When the amounts of substance of all the components are fixed, the system is essentially a closed system. Thus, the Gibbs free energy's partial derivative with respect to temperature with pressure and the amounts of substance of all the components held constant is the opposite of entropy. Similarly, the Gibbs free energy's partial derivative with respect to pressure with temperature and the amount of substance of all the components held constant is volume. Then, we define a new quantity, chemical potential. The chemical potential of a component is the Gibbs free energy's partial derivative with respect to the amount of substance of it, with temperature, pressure, and the amount of substance of all the other components held constants. In other words, the chemical potential is the rate of change of Gibbs free energy of a mixture with respect to the change in the amount of substance of a specific component, when temperature, pressure, and the amounts of substance of other components are fixed. Thus, the exact differential of Gibbs free energy can be expressed in such form. We know that Gibbs free energy is an extensive quantity. So, if the size of the system is multiplied by lambda times with temperature and pressure held constants, the Gibbs free energy is also multiplied by lambda times. Differentiate this equation with respect to lambda. The left side is simply Gibbs free energy. The right side should be calculated with the chain rule in calculus. The result is that the Gibbs free energy of a solution is equal to the sum of the products of the amounts of substances and chemical potentials of all the components. It is another way to express the relationship between Gibbs free energy and chemical potential. Especially, when there is only one component in the solution, its chemical potential is equal to its molar Gibbs free energy. Now, let's consider the phase equilibrium between two phases at certain temperature and pressure. The change of overall Gibbs free energy is the sum of the changes of the Gibbs free energy of the two phases. The change of Gibbs free energy of each phase is caused by the changes of the amounts of substance of the components. Note that the total amount of substance of every component in all phases is fixed. So, the change of its amount of substance in one phase is just the opposite to that in the other phase. Then, the change of Gibbs free energy can be expressed in such form. We know that, at certain temperature and pressure, the Gibbs free energy of the overall closed system never increases. Therefore, if a component's chemical potential is higher in one phase, it diffuses to the other phase spontaneously. When the chemical potentials in all the phases of every component are equal to each other, the system reaches equilibrium and the mass diffusion stops. The concept of chemical potential not only applies to chemical substances, but also electrons. For example, in electronics, the Fermi level is called the chemical potential of electrons. The N-type semiconductor has higher chemical potential than the P-type semiconductor if they are based on a same intrinsic semiconductor. Thus, when a p-n junction is formed, the electrons diffuse from the N-type semiconductor to the P-type semiconductor. Only when the built-in voltage offsets the chemical potential difference between the two parts, the p-n junction is in equilibrium and the electron diffusion stops. We have known that the change of Gibbs free energy of an ideal gas in an isothermal process is determined by its initial and final pressures. We can use the standard state as the initial state, whose chemical potential is its standard chemical potential. Thus, we can calculate the chemical potential of an ideal gas at any pressure with the standard chemical potential as a reference. It can be understood in such way that the chemical potential is based on the standard chemical potential and corrected by the relative concentration to its standard state. This relation can be generalized to all substances, where the relative concentration is replaced by activity. The activity is not exactly equal to relative concentration in most cases, but reflexes the concentration's influence on chemical potential. The activity of a component in an ideal gas mixture is the ratio of its partial pressure to the standard pressure. Please check the example below for the calculation of chemical potential of oxygen in air. An ideal solution is a solution with thermodynamic properties analogous to those of a mixture of ideal gases. In an ideal solution, the intermolecular force between different components is equal to those within a component. For example, the solution of benzene and toluene is almost an ideal solution. The interactions between benzene molecules, between toluene molecules, and between benzene and toluene molecules are almost the same. Similarly, the solution of 1-propanol and 2-propanol is almost an ideal solution as well. The interactions between 1-propanol molecules, between 2-propanol molecules, and between 1-propanol and 2-propanol molecules are almost the same. However, the solution of benzene and 2-propanol is a non-ideal solution. The interaction between benzene and 2-propanol molecules is different from those between benzene molecules and between 2-propanol molecules. Since there is no change in the intermolecular forces, the enthalpy of mixing of ideal solution is 0. Meanwhile, the entropy of mixing also has the same form as that of ideal gases. The expression of entropy of mixing of an ideal liquid-liquid solution is the same as that of a binary ideal gas mixture. As a result, the Gibbs free energy of mixing is also the same as that of binary ideal gas mixture. The Gibbs free energy of such solution is the sum of the Gibbs free energy of the pure liquids and the Gibbs free energy of mixing. The Gibbs free energy of a pure liquid is its amount of substance multiplied by its chemical potential. On the other hand, the overall Gibbs free energy of the solution is equal to the sum of the amounts of substance of the components multiplied by their chemical potentials. The chemical potential of a component is the standard chemical potential corrected by its activity. Meanwhile, the standard state of a liquid component is the pure liquid. Thus, we have another expression of the overall Gibbs free energy. Compare this expression with the previous one. We can find that, in an ideal solution, the activity of a component is equal to its mole fraction. Now, let's consider the phase equilibrium between a liquid phase solution and its vapor. For simplicity, the liquid phase solution is called the solution throughout this section. And the mole fraction only refers to the mole fraction in the solution, rather than in the vapor. In equilibrium, the chemical potentials of a component in the solution and its vapor are equal. Suppose the solution is an ideal solution. The chemical potential of the component is its standard chemical potential as a pure liquid corrected by its mole fraction. Furthermore, suppose the vapor is an ideal gas. The chemical potential of the component is its standard chemical potential as a pure gas at standard pressure corrected by its partial pressure. We also know that, when the component is a pure liquid with mole fraction 1, it is in equilibrium with its vapor at its vapor pressure. Combining the two equations yields the Raoult's law. It states that the partial pressure of a component in the vapor in equilibrium with an ideal solution is proportional to its mole fraction. The proportionality coefficient is its vapor pressure as a pure liquid. For example, the solution of benzene and toluene is close to an ideal solution. When the solution is pure toluene, the partial pressure of toluene is the vapor pressure of toluene. The partial pressure of benzene is 0. The partial pressure of benzene increases linearly with its mole fraction until the vapor pressure of benzene, when the solution becomes pure benzene. Meanwhile, the partial pressure of toluene decreases linearly with its mole fraction until 0, when the solution contains no toluene. The total pressure is the sum of the partial pressures of benzene and toluene, which changes linearly between the vapor pressures of benzene and toluene. Henry's law states that, if the mole fraction of a component is low, its partial pressure is proportional to its mole fraction. The proportionality coefficient is called its volatility. For ideal solution, Henry's law is identical to Raoult's law. That is, the vapor pressure and volatility of a component are the same. For non-ideal solution, the vapor pressure and volatility of a component are different. Here, I show you an example of a non-ideal solution of dimethoxymethane and carbon disulfide. Pay attention, with low mole fractions, both components comply Henry's law. With high mole fractions, both components comply Raoult's law. Like the mole fraction, we can also define the partial pressure fraction. It is the ratio of the partial pressure of a component to the total pressure. For ideal solutions, the partial pressure of a component can be expressed by the Raoult's law. Thus, the ratio between the partial pressure fractions is the product of their ratio of mole fractions and their ratio of vapor pressures. As a result, a more volatile component has higher partial pressure fraction than its mole fraction. For example, in the benzene-toluene system with a mole fraction of 0.5 for both components, the benzene has a higher partial pressure than toluene, consequently, higher partial pressure fraction than toluene. It is because benzene is more volatile than toluene. We know that the vapor pressures depend on temperature. So, the total pressure of a vapor depends on temperature and the composition of the solution. Thus, the temperature at which the solution and its vapor coexist in equilibrium depends on the total pressure and the composition of the solution. The bubble point is the temperature, at a given pressure, where the first bubble of vapor is formed when heating a solution. It is a property of the solution, which is a function of the mole fractions of the components. On the other hand, the mole fractions are related to the partial pressure fractions. So, the temperature at which the vapor and its solution coexist in equilibrium also depends on the total pressure and the composition of the vapor. The dew point is the temperature, at a given pressure, where the first dew of solution is formed when cooling a vapor. It is a property of the vapor, which is a function of the partial pressure fractions of the components. Let's use a CT diagram of 1-propanol, 2-propanol system at standard pressure as an example. 1-propanol and 2-propanol are component 1 and 2 respectively. At low enough temperature, there is only one solution phase, because 1-propanol and 2-propanol are miscible. At high enough temperature, there is only one vapor phase. When the system is pure 1-propanol, the temperature where the vapor and liquid phases coexist in equilibrium is the boiling point of 1-propanol, which is equal to the bubble point and dew point. The bubble point and dew point decrease with the mole fraction of 2-propanol. When the system becomes pure 2-propanol, the temperature where the vapor and liquid phases coexist in equilibrium is the boiling point of 2-propanol, which is also equal to the bubble point and dew point. Between two pure liquids, the bubble point curve and the dew point curve do not overlap. That is because at the temperature where the solution and the vapor phases are in equilibrium, the mole fraction and partial pressure fraction are different. Between the bubble point curve and dew point curve, the solution and vapor phases coexist in equilibrium. The dew point curve is always higher than the bubble point curve. It is because the boiling point of 1-propanol is higher than that of 2-propanol. So, the vapor pressure of 1-propanol is lower than 2-propanol. It is also lower than the total pressure. Thus, the partial pressure fraction of 1-propanol in the vapor is lower than the mole fraction of it. The dew point curve is to the left of the bubble point curve. Furthermore, the bubble point raises with the mole fraction of 1-propanol. So, the dew point curve on the left of bubble point curve is also above it. If we swap the positions of the two components, the dew point curve becomes to the right to the bubble point curve. But the dew point curve is still above the bubble point curve. Imagine, we heat a solution with mole fraction x prime from a low temperature. When the temperature reaches the bubble point at x prime t prime, the solution starts to bubble. The bubble is at the same temperature and is in equilibrium with the solution. So, its partial pressure fraction is y prime at t prime. Pay attention, y prime is not equal to x prime. On the other hand, if we cool a vapor with partial fraction y prime from a high temperature, the vapor starts to dew when the temperature reaches t prime at y prime. And the mole fraction of the dew is x prime. Due to the difference in mole fraction and partial pressure fraction at the same temperature, the components in a solution can be separated. Here, we use the same solution as an example. Suppose the solution has an initial x1 of 0.77. The bubble point of it is 93 degrees Celsius. Meanwhile, the partial pressure fraction of 0.66 has dew point at 93 degrees Celsius. When the initial solution is vaporized, the vapor with partial pressure fraction 0.66 is produced. The vapor can be collected and condensed by lowering the temperature. The new solution has a mole fraction of 0.66. On the other hand, the remaining solution gains a higher mole fraction than the initial solution. This process is called distillation. The new solution can be distilled again to further reduce x1. The distillation can be repeated until a desired fraction is reached. Here, I show you a laboratory fractional distillation setup. The original solution is put into the round bottom flask, and the fractionating column is fitted into the top. As the distance from the still pot increases, a temperature gradient is formed in the column. As the vapor ascends the temperature gradient, some of the vapor condenses on the platforms, known as trays, inside the column and vaporizes. Each time the vapor condenses and vaporizes, the fraction of the more volatile component in the vapor increases. Meanwhile, the fraction of the less volatile component in solution remained on the tray increases. The solution on the trays runs back down into the solution below. This process is called reflux. Eventually, after the distillation along the length of the column, the vapor at the top of the column is composed solely of the more volatile component. It then passes into the condenser, which cools it down until it liquefies. Unlike ideal solutions, some non-ideal solutions form azeotropes at certain compositions. The composition of an azeotrope is identical to its vapor. For example, at standard pressure, methanol and chloroform form an azeotrope when the mole fraction of methanol is about 0.65, where the partial pressure fraction of methanol is also 0.65. The composition of an azeotrope is unchanged by distillation. Thus, it is impossible to separate the components in a solution if azeotrope exists. For example, it is not possible to produce pure ethanol from a water ethanol solution by simple distillation. Please think about the reason by yourself. We know that, for a binary solution, the partial pressure of the solvent depends on the concentration of the solute. As the concentration of the solute increases, the concentration of the solvent decreases. Then, the partial pressure of it decreases. The change of partial pressure of the solvent is proportional to the mole fraction of the solute. It is not difficult to imagine that other properties of the solvent and solution also depend on the concentration of the solute. Colligative properties are those properties of ideal solutions that depend on the concentrations of the solutes, and not on the nature of them. Some typical colligative properties are the changes of the physical properties of the solution. For example, boiling point change, freezing point change and osmotic pressure are proportional to the concentration of the solute. The change of freezing point and the boiling point can be understood by this chemical potential versus temperature plot. Here, we suppose that the solute does neither volatile nor freeze. That is, only the solvent experiences phase transitions. The chemical potential of the solid decreases with temperature at low temperature range. The slope of the tangent to the curve is the opposite of the entropy of the solid. The chemical potential of the liquid decreases with temperature at medium temperature range. The slope of the tangent to this curve is the opposite of the entropy of the liquid. Note that the entropy of the liquid is greater than that of the solid. The two curves have an intersection where the chemical potentials of the solid and liquid are equal, so they are in phase equilibrium. The temperature of the intersection is the freezing point. The chemical potential of the vapor decreases with temperature at high temperature range. The slope of the tangent to the curve is the opposite of the entropy of the vapor. Note that the entropy of the vapor is the greatest. The liquid and vapor curves have an intersection where the chemical potentials of the liquid and vapor are equal, so they are in phase equilibrium. The temperature of the intersection is the boiling point. If some solute is added to the liquid, the chemical potential of the liquid, solvent, decreases. Such change displaces the positions of the intersections. The freezing point lowers, while the boiling point raises. It can be understood in such way. As the chemical potential of the liquid decreases, it becomes more difficult to freeze and boil. Here, we use the calculation of the change of freezing point as an example. At the freezing point, the chemical potential of the solid is equal to that of the solvent in the solution. The chemical potential of the solvent in the solution can be expressed in terms of the mole fraction of the solvent or the solute. When the mole fraction of the solute is low, the logarithm can be approximated by the first-order term of the Taylor series. Rearrange the equation and differentiate it with respect to temperature with pressure held constant. The terms including the chemical potentials can be replaced with Gibbs-Helmholtz equation because the chemical potential of a pure substance is its molar Gibbs free energy. The difference between the molar enthalpies of solid and liquid is the opposite of enthalpy of fusion. Then we use the condition again that the mole fraction of the solute is low. We find that the change of the freezing point decreases proportionally with the mole fraction of the solute because the enthalpy of fusion is positive. One of the applications of the colligative properties is antifreezing. Normal water freezes at 0 degrees Celsius. It makes a lot of troubles in the winter, such as the slippery frozen ground. If the coolant in the vehicle freezes, it no longer works, and can even damage the cooling system. We can use antifreezer to avoid freezing. The main composition of antifreezing coolant is water and ethylene glycol. The plot of freezing point versus the volume fraction of ethylene glycol is shown in the figure. When the fraction of water or ethylene glycol is low, the change of freezing point is proportional to it, which is in accordance with our previous calculation. The particular antifreezer, which decreases the freezing point down to -37 degrees Celsius, contains about 50% ethylene glycol by volume. Osmosis is the spontaneous diffusion of solvent through a semipermeable membrane from a region of high solvent concentration to a region of low solvent concentration. A typical experiment to explain osmosis is shown in the figure. Suppose a U-shaped tube has water in it. Between the left and right arms of the tube, there is a semipermeable membrane, which is permeable to water molecules but blocks bigger molecules. At the beginning, the left and right arms are equivalent. When the system is in equilibrium, the chemical potential of water on the left side of the semipermeable membrane is equal to that on the right side. Then, a solute, such as glucose, is added to the left arm. The solute lowers the concentration and chemical potential of water in the left arm. As a result, water diffuses from the right arm to the left arm through the semipermeable membrane. The pressure of the left arm increases, while the pressure of the right arm decreases. A new equilibrium is established when the chemical potential change due to the solute is offset by the chemical potential change due to the pressure difference. Such pressure difference is so-called osmotic pressure. In the left arm, the chemical potential of water is reduced due to the solute. When the concentration of the solute is low, the chemical potential change is proportional to the mole fraction of the solute, like what we derived in the previous example. Meanwhile, chemical potential raises due to the osmotic pressure. Since the molar volume of liquid hardly changes with pressure, the change of chemical potential due to osmotic pressure is simply molar volume times osmotic pressure. When water on the left side of the semipermeable membrane is in equilibrium with that on the right side, the changes of chemical potentials due to the solute and osmotic pressure must cancel out each other. Then, we can find that the osmotic pressure is proportional to molarity of the solute. Here, we used the assumption that the concentration of the solute is low. So, the amount of substance of the solution is close to that of water. Meanwhile, the volume of the solution is also close to that of water. The formula for osmotic pressure has the same form as the ideal gas law. For example, at 310 Kelvin, the osmotic pressure of normal saline, which contains 0.9% sodium chloride in water by weight, is about 7.83 atm, according to the equation. Pay attention, each mole of sodium chloride contributes 2 moles of particles in saline, because it dissociates into sodium cations and chloric anions. Our blood has an osmotic pressure of 7.25 atm. It seems that the saline has higher osmotic pressure than our blood. However, saline is not an ideal solution. The actual osmotic pressure of normal saline is very close to our blood. That is why we use normal saline in intravenous therapy, eye drops, and to flush wounds and skin abrasions. If a cell is put in a solution which has an osmotic pressure higher than its own, it will shrivel. If it is put in a solution with a lower osmotic pressure than its own, the cell will swell and may even burst. It is also the reason why freshwater fish cannot live in seawater and vice versa. Reverse osmosis is such a process. When an external pressure is applied to the side with higher osmotic pressure, the solvent flows to the other side with lower osmotic pressure. The direction of solvent flow is opposite to osmosis. The reason of reverse osmosis is that, by applying an extra pressure higher than the osmotic pressure, the chemical potential of the solvent raises to an even higher value than the pure liquid. Reverse osmosis is used in seawater purification, that is, desalination. The osmotic pressure of seawater calculated by previous equation is 33.7 bar. The actual seawater osmotic pressure is about 27 bar because seawater is a non-ideal solution. In practice, a 40 to 80 bar pressure is used in seawater desalination to achieve an economic efficiency.